Tonight we're going to explore something you've probably never questioned. Stillness. You've felt it. Sitting alone in a quiet room, everything around you perfectly motionless. The chair beneath you, the walls, the air. Nothing moving, nothing changing. But here's what nobody tells you. That stillness is a lie. It doesn't exist. It has never existed. Not once in the entire 14 billion year history of the universe has any object, any particle, any point in space ever been perfectly still. And this isn't just some technicality or clever wordplay. The laws of physics literally forbid it. The universe was built from the ground up to make absolute stillness impossible. And by the end of tonight, you're going to understand exactly why. And it's going to change how you see everything around you. Before we get into this, if you find these kinds of deep explorations interesting, a quick like or subscribe really helps the channel out. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something familiar. Something you experience every single day of your life, but probably never think about. Sitting still. Right now, wherever you are, you might be sitting in a chair, lying in bed, or standing perfectly motionless. And everything around you seems to confirm what your eyes are telling you. The table is still, the walls are still. The floor beneath your feet is solid, fixed, unmoving. If you placed a glass of water on a table and waited, the water would settle, the ripples would fade, and eventually everything would become perfectly calm, perfectly quiet, perfectly still. Or so it seems, because here's what's actually happening right now, at this very moment, in every object you can see and touch. Every atom in that table is vibrating. Every molecule in that glass of water is tumbling and spinning and colliding with its neighbors millions of times every second. Every particle in the floor beneath you is oscillating back and forth in a frantic, ceaseless dance that has been going on since those atoms first formed billions of years ago. Nothing around you is still, not one single thing. And the reason for this unending motion comes down to something so ordinary, so everyday, that you probably don't even think of it as a force. Heat, temperature, the warmth of the room you're sitting in right now. Let me explain what heat actually is, because most people have a completely wrong picture of it in their heads. When you feel warmth, when you touch something hot or step into a warm room, what you're actually feeling is motion. That's it. That's all heat is. It's the motion of atoms and molecules. The faster they move, the hotter something feels. The slower they move, the colder it feels. Temperature is just a measure of how fast, on average, the particles in a substance are moving. This sounds simple, but it took humanity centuries to figure it out. For a very long time, scientists believed heat was a substance. They called it caloric. The idea was that hot objects contained a fluid called caloric that flowed from hot things to cold things. When you heated a pot of water, you were adding caloric fluid to it. When the water cooled down, the caloric was flowing out. This theory was popular for over 100 years. It was elegant and it seemed to explain a lot of everyday observations. Hot things warming cold things felt exactly like a fluid flowing from one place to another. But caloric theory had problems. Serious problems. In 1798, an American-born physicist named Benjamin Thompson, also known as Count Rumford, was overseeing the boring of cannon barrels in Munich. He noticed something strange. The process of drilling into metal produced an apparently endless supply of heat. The metal shavings were hot. The drill bit was hot. The cannon barrel was hot. And no matter how long the drilling continued, the heat kept coming. If heat were a fluid contained within the ore metal, it should eventually run out. You drain all the caloric from the metal and it would stop producing heat. But that never happened. The drilling could continue indefinitely and the heat never stopped. Thomson realized that the heat wasn't coming from some hidden fluid inside the metal. It was being created by the mechanical motion of the drill. Motion was being converted into heat. This was one of the first strong pieces of evidence that heat wasn't a substance at all. It was a form of motion. But it took another 50 years for this idea to really take hold. In the 1840s, a physicist named James Prescott Joule conducted a famous series of experiments. He built an apparatus where a falling weight turned a paddle wheel inside a container of water. The paddle wheel churned the water, and Joule carefully measured the temperature increase. He showed that a precise amount of mechanical work always produced a precise amount of heat. The relationship was exact and repeatable. Motion could be converted into heat, and the conversion followed strict mathematical rules. Joule had demonstrated what we now call the mechanical equivalent of heat. Work and heat were two forms of the same thing: energy. Around the same time, scientists were developing what we call the kinetic theory of gases. This theory proposed that gases are made up of tiny particles, atoms and molecules, moving in random directions at high speeds. The pressure a gas exerts on the walls of its container isn't caused by some mysterious force. It's caused by trillions of particles physically slamming into the walls every second. Each individual impact is tiny, but there are so many of them happening so fast that the combined effect is a steady, measurable pressure. Temperature in this framework becomes beautifully simple. It's the average kinetic energy of the particles. Kinetic energy is the energy of motion. So temperature literally measures how much motion the particles have. A hot gas has particles moving fast. A cold gas has particles moving slowly. When you heat a gas, you're making its particles move faster. When you cool it, you're slowing them down. This same principle applies to liquids and solids, though the motion looks a bit different. In a gas, particles fly around freely, bouncing off each other and the walls of their container. In a liquid, particles are close together but still move around, sliding past each other, tumbling, rotating. In a solid, particles are locked into fixed positions, but they vibrate. They oscillate back and forth around their fixed positions, jiggling constantly. Even in the hardest, most rigid solid you can imagine, a diamond, a block of steel, a granite countertop, the atoms are vibrating. They're shaking back and forth billions of times every second. You can't feel it because the vibrations are incredibly tiny, smaller than the diameter of an atom, but they're there, always there, never stopping. Let me give you a sense of how fast these vibrations are and how violent the motion really is. Take a room temperature gas like the air you're breathing right now. The nitrogen and oxygen molecules in the air around you are moving at an average speed of about 500 meters per second. That's roughly 1,100 miles per hour. Faster than the speed of sound. Faster than a bullet from many firearms. The air molecules surrounding you right now, the ones touching your skin, entering your lungs, brushing past your face, are screaming past each other at over 1,000 miles per hour. You don't feel this because the molecules are incredibly small and because they're moving in random directions. For every molecule hitting you from the left, another one is hitting you from the right. The forces cancel out on average, so you feel nothing. No wind, no push, just calm, still air. But the calm is an illusion created by averaging trillions upon trillions of chaotic individual motions. In a glass of water at room temperature, the water molecules are moving at about 600 meters per second on average. They're constantly colliding with each other, bouncing off each other, exchanging energy. Each molecule undergoes roughly 10 billion collisions per second. 10 billion. That's 10,000 million collisions every single second for every single molecule. And in a typical glass of water, there are about 8 times 10 to the 24 molecules. That's 8 trillion molecules, each experiencing 10 billion collisions per second. The amount of activity happening in a glass of water sitting quietly on your table is staggering. It makes the busiest highway, the most crowded city, the most chaotic battlefield look utterly peaceful by comparison. Even in solids, where atoms are locked in place, the vibrations are intense. In a piece of iron at room temperature, the iron atoms vibrate at a frequency of about 10 trillion times per second. 10 trillion oscillations every single second. The amplitude is tiny, maybe a few percent the distance between atoms, but the frequency is enormous. If you could somehow hear these vibrations, they'd be far above any frequency your ears could detect, far above any sound any living creature has ever heard. Solids feel rigid and still because the atoms don't move far from their fixed positions, but they're vibrating furiously in place, like a crowd of people standing shoulder to shoulder, each one shivering uncontrollably. Now, let's talk about one of the most beautiful experiments in the history of science. An experiment that proved once and for all that atoms are real and that they're in constant motion. In 1827, a Scottish botanist named Robert Brown was looking through a microscope at pollen grains suspended in water. He noticed something peculiar. The pollen grains were jiggling. They were moving around erratically, tracing random zigzag paths through the water. At first, Brown thought the pollen grains might be alive, that they were somehow swimming or propelling themselves. But then he tried the experiment with particles that were definitely not alive. Ground up glass, dust from rocks, soot. They all did the same thing. Every tiny particle suspended in water jiggled and danced in the same random way. Brown had discovered what we now call Brownian motion, but he couldn't explain it. No one could for nearly 80 years. The jiggling particles remained a mystery, an unexplained phenomenon that fascinated scientists but resisted explanation. Then, in 1905, a young physicist named Albert Einstein published a paper that changed everything. Einstein explained that the jiggling of pollen grains was caused by water molecules. The water molecules were in constant motion due to their thermal energy, and they were constantly bombarding the pollen grains from all sides. Most of the time, the bombardment was roughly equal from all directions, so the pollen grain didn't move much. But occasionally, by pure chance, a few more molecules would hit from one side than the other, giving the pollen grain a tiny kick in one direction. Then, a moment later, the kicks would come from a different direction. The result was the random zigzag motion Brown had observed. Einstein didn't just describe this qualitatively. He worked out the mathematics precisely. He predicted exactly how far a particle should move on average over a given time based on the temperature of the water, the size of the particle, and the viscosity of the liquid. These predictions were tested experimentally by French physicist Jean Perrin in 1908. Perrin painstakingly tracked the positions of tiny particles under a microscope and confirmed that Einstein's predictions were exactly right. This was one of the most important experiments in physics because it provided direct, visible evidence that atoms exist and that they're in constant motion. Before this, many scientists still doubted whether atoms were real or just useful mathematical fictions. Perrine's work settled the debate. Atoms are real, they move, and their motion explains the random jiggling of particles we can see. Perrine won the Nobel Prize in 1926 for this work. Einstein's paper on Brownian motion is sometimes overshadowed by his other famous papers from 1905, the ones on special relativity and the photoelectric effect. But his Brownian motion paper was arguably just as revolutionary because it gave us direct proof of the atomic nature of matter and the ceaseless thermal motion of all particles. So everything around you is in constant motion because of heat. But here's a natural question. What if we could remove all the heat? What if we could cool something down until the atoms stop moving entirely? Is there a temperature at which everything finally becomes perfectly still? This brings us to the concept of absolute zero. The idea of a lowest possible temperature had been around since the 1700s. Scientists noticed that when you cool a gas, its pressure decreases. The relationship is roughly linear. For every degree you cool a gas, the pressure drops by a predictable amount. If you follow this trend down, extrapolating the line to zero pressure, you arrive at a temperature of about minus 273.15 degrees Celsius. This is absolute zero. It's the temperature at which a gas would theoretically exert zero pressure, meaning its particles would have zero kinetic energy. They'd be perfectly still. Scientists developed the Kelvin scale to make this more intuitive. On the Kelvin scale, absolute zero is simply 0 Kelvin. Room temperature is about 293 Kelvin. Water freezes at 273 Kelvin. Water boils at 373 Kelvin. The Kelvin scale starts at the bottom, at the absolute floor of temperature, at the point where, in classical physics, all motion would stop. This idea, absolute zero as the point of perfect stillness, was central to the development of thermodynamics. It made mathematical sense. It fit neatly into the equations. And for a long time, scientists assumed that if you could just cool something enough, you could freeze it into perfect stillness. But here's the first hint that something deeper is going on. No one has ever reached absolute zero. Not even close, actually. Scientists have spent over a century trying. They've developed incredibly sophisticated cooling techniques. Laser cooling, evaporative cooling, magnetic refrigeration, adiabatic demagnetization. Each technique pushes the temperature lower, but the colder you get, the harder it becomes to go further. The third law of thermodynamics, formulated by Walter Nernst in 1906, states that it's impossible to reach absolute zero in a finite number of steps. You can get closer and closer, but you can never actually arrive. This isn't just a practical limitation, like saying you can't build a rocket fast enough. It's a fundamental law of nature. The universe doesn't allow you to reach absolute zero. The temperature can approach it asymptotically, getting closer and closer forever, but never touching it. Today, the coldest temperatures ever achieved in laboratories are in the range of a few hundred trillionths of a Kelvin above absolute zero. In 2003, researchers at the Massachusetts Institute of Technology cooled a gas of sodium atoms to about 450 picokelvin. That's 450 trillionths of a degree above absolute zero. incredibly cold, unimaginably cold, so cold that the atoms were barely moving at all by everyday standards, but they were still moving, still jiggling, still vibrating. Even at these incredibly low temperatures, the atoms had measurable motion. They weren't still. They couldn't be still. And here's where the story starts to get really interesting. You might think the reason scientists can't reach absolute zero is just an engineering problem. Maybe the cooling equipment isn't good enough. Maybe there's always some stray heat leaking in from the environment. If we could just build better insulation, better cooling systems, maybe we could finally get there. But that's not it. The reason you can't reach absolute zero isn't a limitation of our technology. It's a limitation of reality. Even if you could somehow remove every last bit of thermal energy from a system, even if you could cool something to precisely 0 Kelvin, the atoms would still not be perfectly still. They would still be moving, still vibrating. And the reason for this has nothing to do with heat. It has to do with something much deeper. Something that shook the foundations of physics when it was first discovered in the 1920s. Something called quantum mechanics, and specifically something called the Heisenberg uncertainty principle. Let me give you one more example of thermal motion to really drive home how pervasive it is before we move on. Think about outer space, deep space, far from any star. It seems like it should be the coldest, stillest, most motionless place imaginable. And it is cold. The average temperature of space is about 2.7 Kelvin. That's 2.7 degrees above absolute zero. Incredibly cold. But even at this temperature, particles aren't still. Hydrogen atoms drifting through interstellar space at 2.7 Kelvin are still moving at about 250 meters per second. That's roughly 560 miles per hour. Even in the coldest natural environment in the known universe, atoms are still racing around faster than a commercial airliner. And there's something else in space that prevents perfect stillness. The cosmic microwave background radiation. This is the afterglow of the Big Bang, a faint bath of microwave radiation that fills every point in space. It was emitted about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form. That radiation has been traveling through space ever since, cooling as the universe expanded, and it now has a temperature of about 2.725 Kelvin. This radiation is everywhere, literally everywhere. There is no place in the observable universe that isn't bathed in this faint glow. Every particle in the universe is constantly being hit by photons from the cosmic microwave background. Every atom, no matter how far from any star, no matter how deep in intergalactic space, is being nudged, bumped, and jostled by these ancient photons. You cannot escape the cosmic microwave background. You cannot shield yourself from it entirely. It comes from every direction. It fills every cubic centimeter of space. And it means that even in the most remote, most desolate, most empty corner of the universe, perfect thermal stillness is impossible. There is always a minimum temperature. There is always some energy. There is always motion. Consider what happens inside your own body right now. You're a bag of water, essentially. About 60% of your body mass is water, and that water is at body temperature, about 310 Kelvin. At this temperature, the water molecules inside your cells are moving at about 640 meters per second. Every protein in your body is vibrating. Every strand of DNA is flexing and twisting. The molecules that make up your cell membranes are flowing like a two-dimensional liquid. The enzymes that catalyze the chemical reactions keeping you alive, are shaking and vibrating, and that vibration is actually essential for their function. Enzymes need thermal motion to work. They flex and shift shape, allowing molecules to fit into their active sites. Without thermal motion, biology would stop. Life depends on the fact that molecules never hold still. Your very existence is proof that stillness is impossible, because if atoms could be perfectly still, the chemistry that makes you alive wouldn't work. Think about that steel bridge you might drive over on your way to work. It seems like one of the most solid, stable, motionless things in the world. But every iron atom in that bridge is vibrating at roughly 13 trillion times per second at room temperature. The bridge is humming at a frequency far too high for any ear to detect. In summer, when the temperature rises, the atoms vibrate faster and the bridge physically expands. This is why engineers design bridges with expansion joints, those gaps you sometimes feel your car bump over. The gaps allow the bridge to grow and shrink as its temperature changes. A steel bridge can expand by several inches on a hot day compared to a cold night. That expansion is the direct, visible consequence of atoms vibrating harder when they're hotter. Thermal motion isn't some abstract concept locked away in physics textbooks. It has real consequences in the everyday world. It's why ice melts. It's why water evaporates. It's why metals expand when heated. It's why food spoils. It's why rubber bands lose their elasticity over time. All of these everyday phenomena are caused by the restless, ceaseless motion of atoms driven by thermal energy. So here's where we stand. Everything you've ever seen, touched, or felt is made of particles in constant motion. That motion is thermal. It's driven by heat energy. The hotter something is, the faster its particles move. The colder it is, the slower they move. But they never stop. Not in the air around you, not in the deepest reaches of space, not in the coldest laboratory on Earth. The third law of thermodynamics says you can never actually reach absolute zero. And even the coldest temperatures we've achieved, temperatures so close to absolute zero that they would seem to be essentially zero, still show measurable motion. But this raises a profound question. Is this just a practical problem? Is it simply that we haven't cooled things enough? Or is there something deeper going on? What if the universe itself, at its most fundamental level, forbids stillness? What if it's not just hard to make something perfectly still? What if it's actually impossible, even in principle, even with perfect technology, even with infinite time and resources? That's exactly what quantum mechanics tells us. And that's what we're going to explore next. Because when you look at the universe at the smallest scales, when you zoom in past atoms, past nuclei, past protons and neutrons, down to the level where the rules of quantum mechanics take over, you discover something extraordinary. You discover that the universe has a built-in flaw of motion that can never, under any circumstances, be removed. Not by cooling, not by isolating, not by any means whatsoever. The universe was built to vibrate, and we're going to find out exactly why. So we've arrived at a question: if you could somehow cool something all the way to absolute zero, if you could drain every last bit of thermal energy from a system, would the atoms finally stop? Would you achieve perfect, complete stillness? The answer is no. And the reason isn't engineering. It isn't that our equipment isn't good enough, or that some stray heat always leaks in. The reason is far more profound than that. The universe itself, at its deepest structural level, does not allow perfect stillness. It's not a suggestion. It's not a guideline. It's a hard rule written into the very fabric of reality. And the man who discovered this rule was a 23-year-old German physicist who, in doing so, shattered our understanding of what it means to know anything about the physical world. His name was Werner Heisenberg, and in 1927, he published a paper that contained what might be the most important inequality in the history of science. It's called the Heisenberg uncertainty principle. And once you understand it, you will never think about motion and stillness the same way again. But to understand what Heisenberg discovered, we first need to understand the world he was trying to make sense of. Because the 1920s were a time of absolute chaos in physics. Everything scientists thought they knew about how the universe worked was falling apart, and the cracks had started to show almost 30 years earlier. In 1900, a German physicist named Max Planck was trying to solve a specific problem. It had to do with how hot objects glow. When you heat a piece of metal, it starts to glow. First dull red, then bright red, then orange, then yellow, then white. The color tells you the temperature. Physicists had equations that try to predict the exact spectrum of light emitted by a hot object, the exact mix of colors it would produce at any given temperature. But the equations didn't work. Classical physics predicted that a hot object should emit infinite amounts of ultraviolet radiation. This was obviously wrong. Hot objects don't blast out infinite energy. The prediction was so absurd that physicists called it the ultraviolet catastrophe. Planck found a mathematical trick to fix the equations. He assumed that energy wasn't continuous, that it didn't flow smoothly like water. Instead, he proposed that energy came in tiny, discrete packets, which he called quanta. The size of each quantum was determined by the frequency of the light multiplied by a constant, a very small number that we now call Planck's constant. The value of Planck's constant is about 6.626 times 10 to the negative 34 joule seconds. That's an incredibly tiny number. So tiny that in everyday life, the graininess of energy is completely unnoticeable. It's like how a sandy beach looks smooth from an airplane even though it's made of individual grains. The quantum nature of energy is invisible at human scales. But at the scale of atoms and subatomic particles, it changes everything. Planck himself didn't fully understand what he'd done. He thought his quanta were a mathematical convenience, a trick that made the equations work. He didn't necessarily believe that energy was actually quantized in reality, but in 1905, Albert Einstein took Planck's idea seriously. Einstein proposed that light itself comes in quanta, discrete packets of energy we now call photons. A beam of light isn't a smooth, continuous wave. It's a stream of individual particles, each carrying a specific amount of energy determined by the light's frequency. Einstein used this idea to explain the photoelectric effect, the observation that shining light on certain metals causes them to emit electrons. Classical physics couldn't explain why only light above a certain frequency could eject electrons regardless of how bright the light was. Einstein's photon model explained it perfectly. Each photon carries a fixed amount of energy. If that energy is high enough, it can knock an electron free. If not, no amount of photons will do the job. More photons just means more light, not more energy per photon. This was revolutionary. Light, which everyone knew was a wave because it showed interference and diffraction patterns, was also behaving like a stream of particles. It was both, somehow. Then, in 1913, Niels Bohr applied quantum ideas to the atom. The model of the atom at the time was a miniature solar system. a heavy nucleus at the center with electrons orbiting around it like planets orbiting a star. But this model had a fatal flaw. According to classical electromagnetic theory, an electron orbiting a nucleus is an accelerating charged particle. And accelerating charged particles radiate energy. An orbiting electron should continuously emit electromagnetic radiation, lose energy, spiral inward, and crash into the nucleus in a fraction of a second. Every atom in the universe should collapse almost instantly. Obviously, this doesn't happen. Atoms are stable. They last for billions of years. Bohr proposed that electrons can only orbit at specific fixed distances from the nucleus. They can occupy certain orbits, but not others. When an electron is in one of these allowed orbits, it doesn't radiate energy. It just stays there. It can jump from one orbit to another by absorbing or emitting a photon with exactly the right amount of energy. But it can't exist between orbits. It's either in one orbit or another with nothing in between. This worked remarkably well for hydrogen. The predicted energy levels matched experimental observations perfectly. But no one could explain why electrons behave this way. Why should they be restricted to certain orbits? What was the underlying reason? The answer came from an unexpected direction. In 1924, a French physicist named Louis de Broglie made a bold proposal. If light, which everyone thought was a wave, could also behave like a particle, maybe particles could also behave like waves. Maybe electrons, protons, and every other particle had a wave nature. De Broglie proposed that every particle has an associated wavelength that depends on its momentum. The faster a particle moves, the shorter its wavelength. The slower it moves, the longer its wavelength. For everyday objects like baseballs and cars, the wavelength is so incredibly tiny, so unimaginably small, that it's completely undetectable. But for something as light as an electron, the wavelength is on the order of the size of an atom. And at that scale, wave behavior matters enormously. De Broglie's idea explained Bohr's orbits beautifully. An electron orbiting a nucleus is a wave. And for the orbit to be stable, the wave has to fit perfectly around the orbit. It has to complete a whole number of wavelengths as it goes around. If it doesn't, the wave interferes destructively with itself and cancels out. The allowed orbits are the ones where exactly one wavelength, or two wavelengths, or three wavelengths fit around the circumference. This was a stunning insight. Electrons aren't tiny billiard balls orbiting a nucleus. They're waves. Standing waves, specifically, like the vibrations of a guitar string but wrapped around in a circle. And just as a guitar string can only vibrate at certain frequencies, certain harmonics, an electron can only occupy certain orbits. The discrete nature of atomic energy levels isn't arbitrary. It's a consequence of wave mechanics. But this raised a deeply troubling question. If particles are waves, what does that mean? A wave is spread out. It exists over a region of space. A particle is localized. It exists at a specific point. How can something be both? What does it mean for an electron to be a wave? In 1925 and 1926, two different physicists independently developed the mathematical framework to answer this question. Werner Heisenberg developed matrix mechanics in 1925, an entirely different mathematical approach built on observable quantities rather than visual models. Erwin Schrödinger developed wave mechanics in 1926, writing his famous Schrödinger equation that describes how quantum waves evolve over time. The two approaches were later shown to be mathematically equivalent, just different ways of describing the same physics. But Heisenberg went further. He thought deeply about what it means to measure something at the quantum level. And in 1927, he arrived at his revolutionary insight: the uncertainty principle. Heisenberg realized that there are pairs of physical quantities that cannot both be known precisely at the same time. The most famous pair is position and momentum. You cannot simultaneously know exactly where a particle is and exactly how fast it's moving. The more precisely you know one, the less precisely you can know the other. This isn't a limitation of our measuring instruments. It's not that our equipment is too crude to measure both at once. It's a fundamental property of nature. The universe itself doesn't have definite values for both position and momentum simultaneously. The information simply doesn't exist. It's not hidden. It's not there waiting to be found with better instruments. It's genuinely not defined. Let me explain this more carefully because it's easy to misunderstand. In everyday life, you can know both where something is and how fast it's moving at the same time. You can see a car on the highway and simultaneously know its position and its speed. This works because everyday objects are large enough that quantum effects are negligible. The uncertainty involved is so tiny that it's completely unmeasurable. But at the atomic scale, the uncertainty becomes significant. If you try to pin down exactly where an electron is, its momentum becomes uncertain. If you try to pin down exactly how fast it's moving, its position becomes uncertain. The product of the two uncertainties can never be smaller than a specific minimum value related to Planck's constant. This is the uncertainty principle expressed mathematically. The uncertainty in position multiplied by the uncertainty in momentum is always greater than or equal to Planck's constant divided by 4 pi. Now here's where this connects to stillness. Think about what it would mean for a particle to be perfectly still. Perfectly still means the particle is not moving. Not moving means its velocity is exactly zero. If its velocity is exactly zero, then its momentum is exactly zero, because momentum is mass times velocity. If the momentum is exactly zero, then we know the momentum with perfect precision. The uncertainty in momentum is zero. But the uncertainty principle says the product of position, uncertainty, and momentum. Uncertainty must always be greater than a certain minimum value. If the uncertainty in momentum is zero, the only way the product can be above the minimum is if the uncertainty in position is infinite. An infinite uncertainty in position means the particle could be literally anywhere in the universe. It has no defined location. It's everywhere and nowhere at once. Its position is completely undefined. Think about what that means. For a particle to be perfectly still, it would have to have no defined position. It would have to be spread out across the entire universe simultaneously. That's not what stillness looks like. That's not what anything looks like. A particle smeared across all of existence is not still. It's the opposite of still. It's maximally uncertain, maximally undefined, maximally spread out. The uncertainty principle makes perfect stillness logically impossible. If you demand zero motion, you lose all spatial definition. The particle can't be here and still at the same time. It can be here, meaning it has a somewhat defined position, but then it must have some uncertainty in its momentum, which means it must have some motion. Or it can have zero motion, but then it can't be here. It can't be anywhere specific. Perfect stillness requires perfect knowledge of both position and momentum. And the universe doesn't allow that. Not because we're not clever enough to measure it. Not because our instruments aren't precise enough. But because the information literally doesn't exist in nature. The universe is fundamentally, inherently, irreducibly fuzzy at the quantum level. Let me try an analogy that might help. Think about a wave on the ocean. If I ask you where is that wave, you point to a general area. Somewhere over there. But a wave isn't a point. It's spread out. It has a crest and troughs extending over some distance. The question, where is the wave, doesn't have a precise answer. Waves don't have exact locations. Now think about a single water droplet. I can tell you exactly where it is. It's right here at this specific spot. It has a definite position, but it's not a wave. It doesn't have a wavelength or a frequency. These are properties of waves, not droplets. In quantum mechanics, particles are both. They're waves and particles simultaneously. An electron has a wavelength, and it has a position. But because it's a wave, its position can't be perfectly defined. And because it's a particle, its wavelength, which is related to its momentum, can't be perfectly defined either. The more wave-like you make it, giving it a very precise wavelength, and therefore very precise momentum, the more spread out it becomes. Its position becomes increasingly uncertain. The more particle-like you make it, confining it to a very small region of space, the more uncertain its wavelength and momentum become. This isn't a choice the physicist makes, it's a property of waves themselves. It's pure mathematics. If you take any wave and try to compress it into a tiny region of space, you need to add together many different wavelengths. The resulting wave packet is localized, but it contains a spread of wavelengths, meaning a spread of momenta. If you want a single pure wavelength, a single precise momentum, the wave must extend infinitely in all directions. It can't be localized at all. This is called the Fourier transform relationship, and it applies to all waves, not just quantum mechanical ones. The uncertainty principle isn't mysterious or magical, it's a mathematical consequence of the wave nature of matter. Heisenberg illustrated this with the famous thought experiment called the Heisenberg microscope. Imagine you want to measure the position of an electron. To see where it is, you need to bounce a photon off it. To see it precisely, you need to use a photon with a very short wavelength, because the resolution of any observation is limited by the wavelength of the light used. Shorter wavelengths give better resolution and more precise position measurements. But here's the problem. A photon with a shorter wavelength has more energy according to Planck's relation. When this high energy photon bounces off the electron, it kicks the electron, changing its momentum by an unpredictable amount. The more precisely you try to see the electron's position by using shorter wavelength light, the harder you kick it, making its momentum more uncertain. Conversely, if you use a gentle, low-energy photon with a long wavelength to minimize the disturbance to the electron's momentum, the long wavelength gives you poor resolution and you can't determine the electron's position precisely. You can't win. Every possible measurement strategy runs into the same limitation. Improving your knowledge of one quantity inevitably degrades your knowledge of the other. This thought experiment is useful for building intuition, but it can be misleading if taken too literally. The uncertainty principle isn't caused by the act of measurement disturbing the system. That's a common misconception. The uncertainty is there whether you measure anything or not. It's an intrinsic property of quantum systems. An electron doesn't have a definite position and momentum that gets disturbed when you measure it. It genuinely doesn't have definite values for both at the same time. The fuzziness isn't introduced by the observer, it's built into the fabric of reality. This was deeply disturbing to many physicists when it was first proposed. Einstein famously refused to accept it. He spent decades trying to find flaws in quantum mechanics, proposing thought experiments designed to show that the uncertainty principle could be violated. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published what's now known as the EPR paradox, arguing that quantum mechanics must be incomplete because the uncertainty principle led to what Einstein called spooky action at a distance. Einstein believed there must be hidden variables, additional information that we don't know about yet, that would restore certainty and determinism to physics. He believed that God does not play dice, as he famously put it. But Einstein was wrong about this. In 1964, physicist John Bell proposed a mathematical inequality that could distinguish between quantum mechanics and any theory based on hidden variables. If experiments showed that Bell's inequality was violated, it would prove that hidden variables couldn't explain quantum behavior. The experiments were finally carried out decisively in the 1980s by Alan Aspect and his colleagues. Bell's inequality was violated. Quantum mechanics was right. Hidden variables were ruled out. The universe really is fundamentally uncertain at the quantum level. In 2022, Aspect, along with John Clauser and Anton Zeilinger, received the Nobel Prize in Physics for their work, proving that quantum entanglement is real and that local hidden variable theories cannot explain quantum behavior. This was the final nail in the coffin for Einstein's objections. The uncertainty principle isn't a gap in our knowledge, it's a feature of reality. Now let me make something very clear, because this is crucial for understanding why perfect stillness is impossible. The uncertainty principle applies to everything, not just electrons, not just atoms, everything, every particle in the universe, every proton, every neutron, every quark, every photon, every neutrino, every atom, every molecule, everything that exists is subject to the uncertainty principle. For large objects like baseballs and planets, the uncertainty is so incredibly small that it's completely undetectable. The uncertainty in the position of a baseball is smaller than the diameter of a proton. It's so tiny that no measurement could ever detect it. For all practical purposes, large objects behave classically. They can have well-defined positions and momenta simultaneously. But for atoms and subatomic particles, the uncertainty is significant. It determines the structure of atoms, the behavior of semiconductors, the properties of materials, the mechanism of chemical reactions. Quantum uncertainty isn't a minor correction to classical physics. At the atomic scale, it's the dominant effect. It's the reason atoms have the sizes they do. It's the reason matter is stable. It's the reason chemistry works the way it does. Let me show you why atoms are the size they are, because this is a direct consequence of the uncertainty principle, and it beautifully illustrates why stillness is impossible. Consider a hydrogen atom. One proton in the nucleus, and one electron somewhere around it. You might think the electron would minimize its energy by sitting right on top of the proton. After all, opposite charges attract. The closer the electron gets to the proton, the lower the electrical potential energy. So why doesn't the electron just collapse onto the nucleus? Because of the uncertainty principle. If the electron were confined to a very small region of space, right at the nucleus, its position would be very precisely known. But the uncertainty principle demands that if the position uncertainty is small, the momentum uncertainty must be large. A large uncertainty in momentum means the electron could be moving very fast. Fast motion means high kinetic energy. So while confining the electron to a tiny space near the nucleus would lower the potential energy, it would simultaneously increase the kinetic energy by an even larger amount. The atom finds a balance point. The electron settles into a region of space where the total energy, kinetic plus potential, is minimized. This balance point gives the atom its characteristic size, about 1/10,000,000th of a meter. The atom is as small as it can be without the kinetic energy penalty becoming too large. The size of every atom in the universe is determined by the uncertainty principle. Without it, electrons would collapse into nuclei and matter, as we know it, wouldn't exist. There would be no chemistry, no molecules, no life, no stars, no planets, no anything. The uncertainty principle and the motion it guarantees is what gives matter its structure. This is worth emphasizing. The motion of the electron in a hydrogen atom isn't thermal motion. It has nothing to do with temperature. Even at absolute zero, the electron is still moving. It still has kinetic energy. This motion is a direct consequence of the uncertainty principle. You cannot remove it by cooling. You cannot remove it by any means whatsoever. It is the irreducible minimum motion that the universe demands. The electron in a hydrogen atom at absolute zero is moving at about 2,200 kilometers per second. That's about 1% of the speed of light. Not because the atom is hot, not because some external force is pushing it, but because the uncertainty principle forbids it from being still. If the electron stopped, its momentum would be exactly known as zero, and its position would become completely undefined. The atom would cease to exist in any meaningful sense. Motion is what holds atoms together. Stillness would destroy them. There's another way to think about this that involves the wave nature of matter directly. Remember that particles are also waves. An electron in an atom is a standing wave, like a vibrating guitar string. A guitar string can vibrate in different modes. The fundamental mode, the first harmonic, the second harmonic, and so on. Each mode has a different frequency and a different energy. The lowest mode, the fundamental, has the lowest frequency and the lowest energy, but it's still vibrating. A guitar string in its fundamental mode is not still. It's oscillating. It has to be, because that's what a vibrating string does. If it were perfectly still, it wouldn't be vibrating at all, and there would be no standing wave. An electron in an atom works the same way. Its lowest energy state, the ground state, is like the fundamental mode of a vibrating string. It has the lowest possible energy, but is still a wave. It's still oscillating. It still has motion. A wave that isn't moving isn't a wave. It's nothing. The ground state of any quantum system is the lowest energy state, but it always has some energy, some motion. You can't go below the ground state. There's nothing below it. It's the floor. And the floor is not zero. Let me also address a common misconception about the uncertainty principle. People sometimes think that Heisenberg's principle means that the act of measuring disturbs what you're measuring, and that if you could just be more gentle in your measurements, you could get around the limitation. This is wrong. The uncertainty isn't caused by clumsy measurement. It's inherent. Consider a particle in its ground state, just sitting there undisturbed by any measurement. It still has uncertainty in its position and momentum. The wave function, which describes the particle's quantum state, inherently encodes this uncertainty. Even if you never measure the particle at all, even if you leave it completely alone, it still doesn't have a definite position and a definite momentum at the same time. The uncertainty is a property of the particle itself, not a property of our knowledge about the particle. This distinction matters enormously. It's the difference between saying we don't know where the particle is and saying the particle doesn't have a definite position. In classical physics, if you don't know where something is, that's a limitation of your knowledge. The object is somewhere specific, and you just need better information to find it. In quantum mechanics, the object genuinely doesn't have a specific position until something forces it to commit, like an interaction or a measurement. Before that, it exists in a superposition of positions, a spread out wave of possibilities. This is deeply counterintuitive. Our brains evolved to deal with the everyday world where objects have definite locations and definite speeds. We've never had to deal with quantum uncertainty in our daily lives because the effects are too small to notice at human scales. But at the atomic scale, this fuzziness is everything. It determines the structure of matter, the behavior of light, and the impossibility of stillness. Heisenberg's uncertainty principle isn't just a statement about electrons and atoms. It applies to everything in the universe. It applies to the quarks inside protons and neutrons. It applies to the protons and neutrons inside atomic nuclei. It applies to atoms in molecules. It applies to molecules in materials. At every level, there's a minimum uncertainty in position and momentum. And that minimum uncertainty guarantees a minimum amount of motion. This brings us to a profound realization. Perfect stillness isn't just practically impossible. It's not just very difficult to achieve. It's not just that we haven't cooled things enough or haven't found a clever enough way to remove all motion. Perfect stillness is forbidden by the laws of physics. It's incompatible with the fundamental nature of matter. Matter is made of waves, and waves move. That's what waves do. A perfectly still wave is a contradiction in terms. It's like asking for a dry ocean or a dark sun. The words individually make sense, but the combination is nonsensical. The Heisenberg uncertainty principle changed physics forever. It showed that the universe is fundamentally probabilistic at the quantum level. You can calculate the probability of finding a particle in a certain location or with a certain momentum, but you can't predict exactly what you'll find. This bothered many physicists, including Einstein and Schrödinger, who spent years trying to show that quantum mechanics was incomplete. But experiment after experiment has confirmed the uncertainty principle. It's been tested in countless ways over nearly a century, and it has never failed. It is one of the most thoroughly tested and best confirmed principles in all of science, and one of its most direct consequences is that perfect stillness is impossible. The universe has a built-in flaw of motion that cannot be removed by any means. You can cool a system to as close to absolute zero as you want. You can isolate it from every possible external influence. You can wait as long as you like. The particles will still be moving. They'll still have kinetic energy. They'll still be vibrating, oscillating, jiggling. Not because of heat, not because of external disturbances, but because the uncertainty principle demands it. This irreducible minimum motion has a name. It's called zero-point motion, and the energy associated with it is called zero-point energy. It's the energy that remains when everything else has been removed. The energy of the ground state. The lowest possible energy any system can have. And it's not zero. It's never zero. It can't be zero. The universe won't allow it. So let's explore zero-point energy in detail. Let's see how it manifests in real physical systems, how scientists have measured it directly, and how it leads to some of the strangest and most surprising phenomena in all of physics, including a force that emerges from empty space itself, proving that even a perfect vacuum, the most empty thing you can imagine, is not still. Nothing is still. Not atoms, not particles, not even empty space. The universe vibrates at every level, and we're about to find out just how deep that vibration goes. We've now arrived at one of the most extraordinary ideas in all of physics. We've seen that everything around us is in constant thermal motion. Atoms vibrating, molecules tumbling, particles colliding, all driven by heat. We've discovered that even if you could remove all the heat, the Heisenberg uncertainty principle would still forbid perfect stillness. Position and momentum cannot both be exactly known, and therefore motion can never be reduced to zero. But what does this actually look like in practice? What happens to real physical systems when you cool them as close to absolute zero as possible? What motion remains, and how much energy does that remaining motion carry? The answer to these questions leads us to one of the most fascinating and experimentally verified phenomena in quantum mechanics: zero-point energy. The energy that cannot be removed. The vibration that persists when everything else has been stripped away. The restless hum of a universe that refuses to be silent. Let's start with a simple picture. Imagine a ball sitting at the bottom of a bowl. In classical physics, the ball can sit perfectly still at the lowest point of the bowl. It has zero kinetic energy because it's not moving. It has the minimum possible potential energy because it's at the lowest point. Its total energy is at the absolute minimum. It's just sitting there doing nothing. This is what classical physics predicts for any system at its lowest energy state. Complete rest, perfect stillness, zero motion. Now replace the ball with a quantum particle. An atom trapped in a potential well, which is essentially a force field shaped like a bowl that confines the atom to a small region. Physicists model this situation using what's called the quantum harmonic oscillator. It's one of the most important models in all of quantum mechanics because it describes so many real physical systems. Springs, vibrating molecules, atoms and crystals, electromagnetic fields and cavities, even the quantum fields that permeate all of space. The quantum harmonic oscillator describes them all. In classical physics, a harmonic oscillator can have any energy, including zero. A mass on a spring can sit motionless at its equilibrium position with zero energy. But in quantum mechanics, the lowest energy state of a harmonic oscillator is not zero. The ground state energy is 1/2 times Planck's constant times the oscillator's frequency. This is written as 1/2 h bar omega, where h bar is the reduced Planck's constant, and omega is the angular frequency. This ground state energy is the zero-point energy. It's the minimum energy the system can have. You cannot extract it. You cannot cool it away. You cannot drain it by any physical process. It's simply the lowest possible energy, and it's always greater than zero. Let me put this in concrete terms. Consider a single atom in a crystal lattice. The atom sits in a potential well created by the electromagnetic forces from its neighboring atoms. It behaves like a tiny mass on a spring. At high temperatures, the atom vibrates vigorously, bouncing back and forth with large amplitude. As you cool the crystal, the vibrations get smaller. The atom moves less. At extremely low temperatures, the thermal vibrations become negligible. But the atom never stops vibrating. At absolute zero, it still oscillates with an amplitude determined by its zero-point energy. This zero-point vibration is small, but it's real and measurable. How small? For a typical atom in a solid at absolute zero, the zero-point vibration has an amplitude of roughly 5 to 10% of the distance between neighboring atoms. That might not sound like much, but it's enormous by quantum standards. The atom is jiggling back and forth over a distance that's a significant fraction of the spacing between atoms. And it does this forever. Not because something is pushing it, not because heat is driving it, but because the uncertainty principle demands it. If the atom were perfectly still at the bottom of its potential well, its position and momentum would both be exactly known. That's forbidden. So the atom vibrates with just enough motion to satisfy the uncertainty principle. No more and no less. It's the minimum amount of motion the universe will tolerate. Now, let me show you the most dramatic and beautiful example of zero-point energy in action. An example that stunned physicists when they first observed it, and that remains one of the clearest demonstrations that the quantum world is fundamentally different from our everyday experience. Liquid helium. Helium is the second lightest element. A helium atom consists of a nucleus with 2 protons and 2 neutrons, surrounded by 2 electrons. It's a noble gas, meaning it doesn't form chemical bonds with other atoms. It's chemically inert. At room temperature and normal pressure, helium is a gas. As you cool it, it remains a gas far below the temperatures where most other substances have long since solidified. Nitrogen freezes at 63 Kelvin. Oxygen freezes at 54 Kelvin. Hydrogen freezes at 14 Kelvin. But helium doesn't liquefy until 4.2 Kelvin. That's just 4.2 degrees above absolute zero. It's the last element to surrender to the cold and become liquid. But here's the truly remarkable thing. Under normal atmospheric pressure, helium never freezes. Never. You can cool it all the way down to absolute zero and it remains a liquid. Every other substance in the universe becomes a solid if you cool it enough. Water freezes, iron freezes, even hydrogen freezes. But helium at normal, pressure stays liquid all the way to absolute zero. Why? Because of zero-point energy. Helium atoms are very light, and because of their low mass, they have a relatively large zero-point energy. This energy keeps them jiggling even at absolute zero. The jiggling is so vigorous that the weak attractive forces between helium atoms, called van der Waals forces, cannot hold them in a fixed crystalline structure. The atoms vibrate too much to settle into a rigid lattice. They stay liquid, sloshing and flowing even at the lowest possible temperature. The zero-point motion literally prevents the atoms from freezing. To make helium solidify, you need to apply pressure. About 25 atmospheres of pressure at absolute zero will finally squeeze the atoms close enough together that the attractive forces can overcome the zero-point motion and lock them in place. But at normal pressure, helium remains a quantum liquid forever. This was first observed experimentally by the Dutch physicist Heike Kamerlingh-Onnes, who was the first person to liquefy helium in 1908. Onnes spent years developing the technology to reach these incredibly low temperatures. He won the Nobel Prize in 1913 for his work on the properties of matter at low temperatures. But the story of helium gets even stranger. Below about 2.17 Kelvin, liquid helium undergoes a dramatic transformation. It becomes what's called a superfluid. Superfluid helium has properties that seem almost magical. It flows with zero viscosity, absolutely zero. This means it can flow through the tiniest cracks and capillaries without any resistance whatsoever. If you put superfluid helium in a cup, it will climb up the walls of the cup, over the rim, and down the outside, dripping onto the table below. It does this because the helium film on the walls of the cup can flow without friction, and surface forces pull it upward. Superfluid helium can also flow through channels so narrow that no normal liquid could pass through them. Channels just a few atoms wide offer zero resistance to superfluid flow. If you set superfluid helium spinning in a container, it will continue spinning forever. Not for a long time, forever. The rotation never slows down because there's no viscosity to dissipate the energy. These bizarre properties are a direct consequence of quantum mechanics operating at a macroscopic scale. Superfluidity occurs because at very low temperatures, a large fraction of helium atoms fall into the same quantum ground state. They form what's called a Bose-Einstein condensate, a state of matter where quantum effects become visible at scales you can see with your naked eye. The 0-point energy that keeps helium liquid is the same energy that allows it to enter this extraordinary superfluid state. Without 0-point energy, helium would freeze like everything else, and none of these phenomena would occur. Now, let's leave atoms behind and talk about something even more astonishing: the 0-point energy of empty space itself. Because it turns out that even a perfect vacuum, a region of space with absolutely nothing in it, no atoms, no molecules, no radiation, no particles of any kind, is not still. It's not empty. It's seething with activity. This sounds paradoxical. How can empty space have energy? How can nothing be doing something? The answer comes from quantum field theory, which is the framework that combines quantum mechanics with special relativity. In quantum field theory, the fundamental entities aren't particles, they're fields. There's an electron field that permeates all of space, a photon field, a quark field, fields for every type of particle. What we call particles are actually excitations of these fields, like ripples on a pond. When we say there's an electron somewhere, we mean the electron field is excited at that location. When we say there's a photon, we mean the electromagnetic field has a ripple in it. Now here's the key insight. Each of these quantum fields behaves like a collection of harmonic oscillators. At every point in space, for every possible wavelength, the field can vibrate. And just like any quantum harmonic oscillator, each of these modes has a 0-point energy of 1/2 h bar omega. Even in the vacuum state, even when no particles exist, every mode of every field has this irreducible minimum energy. The vacuum isn't empty, it's the ground state of all quantum fields simultaneously. And that ground state has energy. Lots of energy, actually. If you try to add up the 0-point energy of all the modes, of all the fields at every point in space, you get a number that's technically infinite. This is one of the great unsolved problems in physics. The naive calculation gives an energy density so enormous that it should cause the universe to curve in on itself. The predicted vacuum energy density is roughly 120 orders of magnitude larger than what we observe. That's 10 to the 120th power times too big. This is sometimes called the worst prediction in the history of physics. Clearly something is wrong with the naive calculation, but physicists haven't fully figured out what. The vacuum energy problem remains one of the deepest mysteries in theoretical physics. But the fact that the vacuum has 0-point energy is not in dispute. We've measured it directly. The most famous experimental demonstration is the Casimir effect, predicted by Dutch physicist Hendrik Casimir in 1948. Casimir realized that if you place two perfectly flat, uncharged metal plates very close together in a vacuum, the plates will be pushed toward each other by a measurable force. Here's why. In the space outside the plates, vacuum fluctuations of the electromagnetic field can have any wavelength. Every possible mode contributes its 0-point energy. But between the plates, only certain wavelengths are allowed. The electromagnetic waves between the plates must fit between them, just like standing waves on a guitar string must fit between the fixed ends. Wavelengths that don't fit are excluded. This means there are fewer modes of vibration between the plates than outside. Fewer modes means less zero-point energy between the plates. The energy density is lower between the plates than outside. This difference in energy density creates a net force pushing the plates together. The vacuum itself is pushing them. The Casimir force is incredibly small. For two plates separated by about 1 micrometer, 1/1,000,000th of a meter, the force is roughly 100 of a millinewton per square meter. That's tiny, but it's measurable with sensitive equipment. In 1997, physicist Steve Lamoureux at the University of Washington performed a precise measurement of the Casimir force using a torsion pendulum. His results match Casimir's theoretical predictions to within 5%. Since then, many other experiments have confirmed the effect with increasing precision. The Casimir effect is real, measurable, and it proves that the vacuum has zero-point energy. Empty space is not empty. It's alive with quantum fluctuations that exert real, measurable forces on physical objects. The implications of this are staggering. It means that there is no such thing as truly empty space. Even if you could remove every atom, every photon, every particle of radiation, every gravitational wave, every neutrino, every cosmic ray, everything, from a region of space, that region would still not be still. The quantum fields would still be fluctuating. Virtual particles would still be popping in and out of existence. The vacuum would still have energy. Let me explain what virtual particles are, because they're another fascinating consequence of vacuum zero-point energy. The uncertainty principle doesn't just apply to position and momentum. There's an analogous uncertainty relation between energy and time. The more precisely you know the energy of a system, the longer you need to measure it. Conversely, over very short time intervals, the energy of a system can fluctuate by large amounts. This means that over very brief moments, enough energy can appear from nowhere to create particle-antiparticle pairs. An electron and a positron, for example, can spontaneously pop into existence from the vacuum, but they can't stick around. The borrowed energy must be returned quickly. The particles annihilate each other almost immediately, vanishing back into the vacuum. These fleeting particles are called virtual particles. They exist for incredibly short times, so short that you can't directly observe them as individual particles. But their collective effects are measurable. The Casimir effect is one such effect. Virtual photons popping in and out of existence between the metal plates are what create the difference in energy density that produces the Casimir force. Another measurable effect of vacuum fluctuations is the Lamb shift, first measured by Willis Lamb and Robert Rutherford in 1947. The Lamb shift is a tiny difference in the energy levels of a hydrogen atom that classical theory and even basic quantum mechanics can't explain. The electron in a hydrogen atom interacts with the virtual particles popping in and out of existence in the vacuum. These interactions slightly shift the electron's energy levels. The shift is incredibly small, about 1 part in a million, but Lamb measured it with extraordinary precision using microwave spectroscopy. The Lamb shift was one of the key experimental results that drove the development of quantum electrodynamics, the quantum theory of electromagnetic interactions. When theorists like Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga developed QED, They calculated the Lamb shift from first principles and got results that matched experiment to better than 1 part in a billion. This is one of the most precise agreements between theory and experiment in all of science, and it's a direct consequence of vacuum fluctuations. The restless churning of empty space measurably affects the energy levels of atoms. Yet, another effect of vacuum fluctuations is the anomalous magnetic moment of the electron. An electron behaves like a tiny magnet, and its magnetic strength can be measured extremely precisely. Classical theory and basic quantum mechanics predict a certain value, but the actual measured value is slightly different. The difference comes from the electron interacting with virtual particles in the vacuum. Photons, electron-positron pairs, even heavier virtual particles all contribute tiny corrections. When you add up all these contributions using quantum electrodynamics, the theoretical prediction matches the experimental measurement to 12 decimal places. 12 decimal places. That's like predicting the distance from New York to Los Angeles and being accurate to within the width of a human hair. This level of agreement is only possible because vacuum fluctuations are real and our theory of them is extraordinarily accurate. Let me come back to zero-point energy in material systems because the consequences extend far beyond individual atoms. In crystals, zero-point energy affects how atoms arrange themselves. It influences the crystal structure, the lattice spacing, and the material's density. In some materials, particularly those made of light atoms like hydrogen, lithium, or helium, zero-point energy has a significant effect on the material's properties. Hydrogen molecules in a solid crystal vibrate so much at absolute zero that the crystal is noticeably less dense than it would be without zero-point motion. Diamonds have a specific heat capacity at very low temperatures that can only be explained by accounting for zero-point vibrations. Even the melting points of certain materials are affected by zero-point energy. In metals, the electrons that carry electrical current have zero-point energy. These electrons exist in quantum states described by the Fermi-Dirac distribution. Even at absolute zero, electrons in a metal are not still. They occupy energy states up to a maximum called the Fermi energy, and they're moving at speeds of about 1% of the speed of light. This might seem bizarre. A metal at absolute zero with its electrons zipping around at enormous speeds. But this is exactly what happens. The electrons can't all be in the same lowest energy state because of the Pauli exclusion principle, which says no two fermions can occupy the same quantum state simultaneously. So the electrons stack up, filling energy states from the bottom up, and even the highest occupied states have substantial energy. These energetic electrons are responsible for many of the properties of metals, including their ability to conduct electricity and heat. Without zero-point energy, metals wouldn't be metals. In nuclear physics, zero-point energy plays a crucial role inside. Atomic nuclei. Protons and neutrons inside a nucleus are confined to a tiny space, roughly 1 femtometer in radius. That's 1 quadrillionth of a meter. Because they're confined to such a small region, the uncertainty principle demands large momentum uncertainty, which means large kinetic energy. The nucleons inside a nucleus are bouncing around at speeds of roughly 60,000 to 75,000 kilometers per second, about 20 to 25% of the speed of light. Not because the nucleus is hot. The nucleus could be at absolute zero, and the nucleons would still be moving this fast. This zero-point kinetic energy is a major component of nuclear binding energy. It's part of what determines which nuclei are stable and which are radioactive. It helps explain why certain isotopes decay and others don't. The stability of matter itself depends in part on the balance between the zero-point kinetic energy of nuclear particles and the strong nuclear force holding them together. Zero-point energy even has implications at the larger scales. Cosmologists believe that vacuum energy, the zero-point energy of quantum fields throughout all of space, might be responsible for the accelerating expansion of the universe. In 1998, two teams of astronomers discovered that the expansion of the universe is speeding up, not slowing down as everyone expected. Something is pushing space apart, counteracting the gravitational attraction of all the matter in the universe. This something is called dark energy, and it makes up about 68% of the total energy content of the universe. One candidate for dark energy is vacuum energy, the zero-point energy of empty space. If space itself has a small but positive energy density, that energy would create a repulsive gravitational effect that pushes space apart. The problem, as I mentioned earlier, is that the naive theoretical prediction for vacuum energy density is absurdly large, about 10 to the 120th power times larger than the observed value of dark energy. This discrepancy is sometimes called the cosmological constant problem, and it's considered one of the greatest unsolved problems in fundamental physics. Either our calculation of vacuum energy is wrong in some deep way, or there's some unknown mechanism that cancels almost all of it, leaving just the tiny residual that drives cosmic acceleration. Either way, the connection between zero-point energy and the fate of the entire universe is one of the most profound links in all of physics. The same quantum restlessness that prevents a helium atom from freezing might be the force that determines the ultimate destiny of the cosmos. Let me give you one more example that drives home just how real and how strange zero-point energy is. The phenomenon is called quantum tunneling, and it's a direct consequence of the fact that particles always have some minimum kinetic energy and that their positions are always somewhat uncertain. In classical physics, if a ball doesn't have enough energy to roll over a hill, it stays on its side of the hill. The hill is a barrier that the ball cannot cross. End of story. But in quantum mechanics, a particle can pass through a barrier even if it doesn't have enough energy to go over it. Because the particle's position is uncertain, there's a small but non-zero probability that the particle is actually on the other side of the barrier, and if it's on the other side, then it is effectively tunneled through. Quantum tunneling is not a theoretical curiosity. It's essential for life. The sun shines because of quantum tunneling. In the sun's core, hydrogen nuclei, which are just protons, fuse together to form helium. But protons are positively charged, and positive charges repel each other. The electrical repulsion between two protons creates an energy barrier that the protons don't have enough thermal energy to overcome. At the sun's core temperature of about 15 million Kelvin, protons move fast but not fast enough to breach this barrier through classical means alone. If classical physics were the whole story, the sun wouldn't shine, nuclear fusion wouldn't happen, stars wouldn't exist, but quantum tunneling allows protons to pass through the barrier with a small but sufficient probability. The zero-point jitter of the protons, combined with their wave nature, gives them a chance to appear on the other side of the barrier and fuse. The rate of fusion is low for any individual pair of protons, but the sun contains an enormous number of protons. Even a small tunneling probability multiplied by a colossal number of attempts per second produces enough fusion reactions to power the sun. Every photon of sunlight that warms your face, every ray of light that drives photosynthesis, Every calorie of energy that sustains life on Earth exists because particles cannot be still. Because quantum uncertainty gives them the jitter they need to tunnel through barriers that classical physics says are impassable. So here's where we stand. 0-point energy is the energy that remains when all thermal energy has been removed. It's the ground state energy of quantum systems, and it's always greater than zero. It manifests as the irreducible vibration of atoms and crystals, the refusal of helium to freeze, the measurable force between metal plates in a vacuum, the shifts in atomic energy levels caused by virtual particles, the motion of electrons in metals at absolute zero, the kinetic energy of nucleons inside atomic nuclei, and possibly the mysterious dark energy driving the accelerating expansion of the universe. It enables quantum tunneling, which powers the stars and makes life possible. 0-point energy is not speculative. It's not theoretical. It's measured, confirmed, and woven into the fabric of everything we observe. The universe has a floor of energy, a basement level below which nothing can go. And that floor is vibrating, always restless, always in motion. Even the emptiest, coldest, most isolated point in the universe is shimmering with quantum activity. The vacuum itself hums with energy that can never be silenced. Nothing is still, not atoms, not empty space, not even nothing itself. And in our final part, we're going to zoom all the way out and see that this restlessness isn't confined to the quantum world. It extends to every scale in the universe. From the jittering of quarks inside protons to the rotation of galaxies to the expansion of space itself, the universe is motion. It has always been motion, and it will never, ever stop. We've spent this journey zooming in. We started at the human scale, where everything seems still. We dove into thermal motion, the frantic vibration of atoms driven by heat. We plunged deeper into quantum mechanics, where the Heisenberg uncertainty principle forbids perfect stillness at the most fundamental level. We explored 0-point energy, the irreducible vibration that persists even at absolute zero, even in empty space. We've seen that stillness is forbidden from the bottom up. The universe has a built-in floor of motion that nothing can breach. But now, let's change direction. Let's zoom out. Let's leave the quantum world behind and look at every scale of the universe. From the particles inside atoms all the way to the expanding cosmos itself. Because what we're going to discover is that restlessness isn't just a quirk of quantum mechanics. It's the defining feature of the universe at every single scale. Nothing is still. Not at the smallest scales, not at the largest, not anywhere in between. Motion is not something the universe does occasionally. Motion is what the universe is. Let's start inside the atom, at the very smallest scales we know about. We've already talked about electrons. They occupy fuzzy probability clouds around the nucleus, never sitting still, always jittering with 0-point motion. But the nucleus itself is just as restless. A typical atomic nucleus is made of protons and neutrons packed together in a space about 1 femtometer across. As we have already seen, the uncertainty principle forces these nucleons into furious motion. But what we haven't yet explored is what that motion actually looks like from the inside. The protons and neutrons aren't just vibrating in place, they're bouncing off each other, interacting through the strong nuclear force, exchanging particles called pions in a constant frenzied dance. The nucleus is not a calm, stable collection of particles sitting neatly together. It's a roiling, dynamic system held together by the strongest force in nature. The strong force which is about 100 times stronger than electromagnetism. Without this force constantly pulling the nucleons back together, the electrical repulsion between the positively charged protons would blow the nucleus apart in an instant. But we can go even deeper. Protons and neutrons are not fundamental particles. They're made of quarks. Each proton contains 2 up quarks and 1 down quark. Each neutron contains 1 up quark and 2 down quarks. These quarks are bound together by particles called gluons, which carry the strong force. And the interior of a proton is one of the most violent, chaotic environments in the known universe. Quarks inside a proton are moving at speeds close to the speed of light. The gluons that bind them are constantly being created and destroyed. Virtual quark-antiquark pairs pop in and out of existence continuously. The inside of a proton is a seething soup of quarks, antiquarks, and gluons, all interacting at nearly the speed of light. In fact, most of the proton's mass doesn't come from the quarks themselves. The 3 quarks in a proton have a combined rest mass of only about 9.4 mega electron volts. But the proton's total mass is about 938 mega electron volts. Where does the other 99% come from? It comes from the kinetic energy of the quarks and gluons, and from the energy stored in the gluon field itself. The mass of a proton, and therefore most of the mass of everything you've ever touched, is not the mass of its constituent parts. It's the energy of their motion. Your body weight is overwhelmingly the energy of quarks moving at near light speed inside your protons and neutrons. You are literally made of motion. Strip away the motion and you'd weigh almost nothing. There's another particle that perfectly illustrates the impossibility of stillness. The neutrino. Neutrinos are ghostly particles that barely interact with anything. They're produced in nuclear reactions, like those in the sun's core, and in radioactive decays. They have almost no mass, far less than an electron, and they interact only through the weak nuclear force and gravity. Because they interact so weakly, neutrinos pass through matter as if it weren't there. Right now, about 65 billion neutrinos from the sun are passing through every square centimeter of your body every second. They go straight through you, straight through the Earth, and out the other side without hitting anything. But the point is this: neutrinos are never still. They travel at speeds extremely close to the speed of light. Because their mass is so tiny, even a small amount of energy sends them racing through space at nearly the maximum speed the universe allows. And they're everywhere. The universe is filled with a background of neutrinos left over from the Big Bang, called the cosmic neutrino background. These relic neutrinos have cooled to a temperature of about 1.95 Kelvin, making them the coldest known particles in the universe. But even at this incredibly low temperature, they're still moving at thousands of kilometers per second. Even the coldest particles in the universe are racing through space at tremendous speeds. Now let's step up from subatomic particles to atoms and molecules. We've already covered thermal motion extensively, so I won't repeat that. But let me add something we didn't cover before. The motion of atoms isn't just random vibration. In many systems, atoms undergo specific, structured types of motion that are essential for the behavior of the materials they make up. In a crystal, atoms vibrate around fixed positions, but these vibrations aren't independent. Each atom's motion affects its neighbors because they're connected by electromagnetic forces. The vibrations propagate through the crystal as waves called phonons. A phonon is essentially a quantum of sound, a collective vibration that travels through the material. At any given moment, a crystal contains billions of phonons bouncing around inside it, reflecting off surfaces, scattering off impurities, interacting with each other. Even at absolute zero, there are still 0-point phonons present. Quantum vibrations that can never be frozen out. Phonons carry heat through materials. They're responsible for thermal conductivity in insulators and semiconductors. They affect how electrons move through metals. They determine how materials absorb sound. The world of phonons is a world of ceaseless organized motion that exists in every solid object around you right now. In liquids, molecules aren't locked in place. They move around, sliding past each other, rotating, vibrating internally. Water molecules at room temperature perform a chaotic tumbling dance, rotating completely about once every picosecond. That's 1/1,000,000,000th of a second. In that same picosecond, each water molecule collides with its neighbors roughly 10 times. The interactions are incredibly rapid and incredibly violent on a molecular scale. Hydrogen bonds between water molecules form and break trillions of times per second. The structure of liquid water is not fixed. It's a constantly shifting, flickering network of bonds that rearranges itself billions of times faster than you can blink. Even in biological systems, motion is not just present but essential. Protein molecules in your cells are in constant thermal motion. They flex, twist, and vibrate. This motion isn't random noise that the protein has to overcome. It's functional. Enzymes rely on thermal fluctuations to open and close their active sites, allowing substrate molecules to enter and products to leave. Molecular motors like kinesin, which transport cargo along microtubules inside cells, walk step by step using a combination of chemical energy and thermal motion. DNA doesn't sit rigidly in the nucleus. It breathes, with the two strands of the double helix constantly opening and closing locally, driven by thermal fluctuations. This breathing motion is essential for DNA replication and gene expression. Life doesn't just tolerate molecular motion, it harnesses it. Biology is built on restlessness. Now, let's scale up dramatically. Let's leave the molecular world and look at the planet beneath your feet. Earth seems like the very definition of solid, stable ground, but Earth is anything but still. Start with the most obvious motion. Earth is rotating. It spins on its axis once every 23 hours and 56 minutes. At the equator, this rotation carries you eastward at about 1,670 kilometers per hour. That's faster than the speed of sound. You're moving at supersonic speeds right now, and you don't feel a thing because everything around you is moving at the same speed. But Earth doesn't just rotate, it also orbits the sun. Earth travels around the sun at an average speed of about 107,000 kilometers per hour. That's roughly 30 kilometers per second. In the time it took you to read this sentence, Earth moved about 200 kilometers through space. Every year, Earth completes one orbit, traveling a total distance of about 940 million kilometers. You've never been in the same place twice. Every moment you're in a new location in space, carried along by Earth's orbit at tremendous speed. But even the ground beneath you, the seemingly motionless solid rock of Earth's surface, is moving. Earth's tectonic plates are in constant motion, driven by convection currents in the mantle. The mantle is the thick layer of hot rock between Earth's crust and core. It's solid, but over long timescales, it flows like an incredibly viscous fluid. Heat from the core drives slow convection currents in the mantle, and these currents drag the tectonic plates along at speeds of about 2 to 10 centimeters per year. That's roughly the speed your fingernails grow. It sounds slow, and it is slow by human standards. But over millions of years, it moves continents. 200 million years ago, all the continents were joined in a single supercontinent called Pangaea. Since then, tectonic motion has split Pangaea apart and shuffled the continents into their current positions. The Atlantic Ocean didn't exist 200 million years ago. It was created entirely by the slow, relentless motion of the tectonic plates. This motion also creates earthquakes and volcanoes. When plates collide, one can be forced beneath the other in a process called subduction. The descending plate melts, and the resulting magma rises to create volcanoes. When plates slide past each other, stress builds up along the boundary until it's released suddenly as an earthquake. The Himalayas, the tallest mountains on Earth, are still growing as the Indian plate pushes into the Eurasian plate at about 5 centimeters per year. Mount Everest gets a few millimeters taller each year. The solid ground beneath you is in slow but perpetual motion, reshaping the surface of the planet over geological timescales. Deep inside Earth, the motion is even more dramatic. Earth's outer core is a layer of liquid iron and nickel about 2,200 kilometers thick. This liquid metal is churning, driven by heat from the inner core and by Earth's rotation. The convection currents in the outer core generate Earth's magnetic field through a process called the geomagnetic dynamo. Without this churning motion, Earth would have no magnetic field. Without the magnetic field, the solar wind would strip away our atmosphere over millions of years, just as it stripped away the atmosphere of Mars when Mars lost its magnetic field. The protection that allows life to exist on Earth's surface depends on the ceaseless motion of liquid iron thousands of kilometers beneath your feet. Earth's inner core is solid iron, compressed by the immense pressure of everything above it. But even the inner core isn't still. It rotates slightly faster than the rest of the planet, spinning independently at a rate that differs from Earth's surface rotation by a tiny amount. The inner core also grows over time as liquid iron from the outer core solidifies onto it, releasing heat that drives the convection above. The entire interior of Earth is a dynamic, churning, moving system. From the tectonic plates on the surface to the liquid iron dynamo in the outer core to the slowly growing inner core, nothing is still. Now let's leave Earth entirely and look at the solar system. Earth orbits the Sun at 30 kilometers per second, but the other planets are moving too. Mercury races around the Sun at about 47 kilometers per second. Venus orbits at 35 kilometers per second. Mars at 24, Jupiter at 13, Saturn at nearly 10. Every planet, every moon, every asteroid, every comet in the solar system is in constant orbital motion. The moons orbit their planets. The planets orbit the Sun. Asteroids tumble and spin as they follow their own paths. Comets streak through the inner solar system on elongated orbits that take them from the frozen outer reaches to the blazing neighborhood of the Sun and back. Even the Sun itself isn't still. The Sun rotates, completing one rotation about every 25 days at its equator. But because the Sun is a ball of plasma, not a solid body, different parts rotate at different speeds. The equator rotates faster than the poles. This differential rotation creates complex magnetic field patterns that drive sunspots, solar flares, and coronal mass ejections. The sun's surface is a turbulent, churning sea of hot plasma. Convection cells called granules cover the surface, each one about 1,000 kilometers across, rising and falling as hot plasma wells up from below and cooler plasma sinks back down. Each granule lasts about 8 to 20 minutes before being replaced by a new one. The sun's surface is never the same from one moment to the next. The sun also moves through the galaxy. Our entire solar system orbits the center of the Milky Way at a speed of about 230 kilometers per second. That's roughly 828,000 kilometers per hour. At this speed, the sun takes about 225 million to 250 million years to complete one orbit. Astronomers call this period a galactic year, or cosmic year. The last time the sun was in its current position relative to the galactic center, dinosaurs were just beginning to appear on Earth. In the time since the sun formed 4.5 billion years ago, it has completed roughly 20 orbits around the galaxy. And it has never once been in the same place twice because the galaxy itself is also moving. The Milky Way is falling toward the Andromeda galaxy at about 110 kilometers per second. In about 4.5 billion years, the two galaxies will collide and merge into a single large elliptical galaxy. But the Milky Way isn't just moving toward Andromeda. Along with the entire local group of about 50 galaxies, we're being pulled toward the Virgo cluster at several hundred kilometers per second. And the Virgo cluster, along with everything else in the Laniakea supercluster, is moving toward a massive concentration of matter called the Great Attractor at about 600 kilometers per second. That's over 2 million kilometers per hour. Every galaxy, every star, every planet, every atom in the Laniakea supercluster is streaming through space at over 600 kilometers per second toward a region we can barely see because it's hidden behind the plane of the Milky Way. And beyond the Great Attractor, the motion continues. The Shapley supercluster, an even larger concentration of galaxies, appears to be pulling Laniakea and everything in it. At the largest scales, the universe is a vast web of matter in motion. Galaxy clusters sliding along cosmic filaments. Superclusters falling toward even larger concentrations of mass. Voids expanding as matter drains out of them. The cosmic web is not a static structure, it's dynamic, evolving, changing over billions of years as gravity pulls matter together and dark energy pushes space apart. And speaking of space itself, here's perhaps the most profound motion of all. Space is expanding. The universe has been expanding since the Big Bang 13.8 billion years ago. Every point in space is getting farther from every other point. Galaxies aren't moving through space away from each other. Space itself is stretching, carrying the galaxies along with it. The expansion of space means that the distance between distant galaxies is increasing over time. The farther away a galaxy is, the faster the distance between us grows. For galaxies more than about 14 billion light-years away, the space between us is expanding faster than the speed of light. This doesn't violate relativity because the galaxies aren't moving through space faster than light. Space itself is expanding, and there's no speed limit on the expansion of space. The expansion rate is described by the Hubble constant, which is currently measured at about 67 to 74 kilometers per second per megaparsec. This means that for every megaparsec of distance, about 3.26 million light-years, galaxies are receding from us at an additional 67 to 74 kilometers per second. A galaxy 100 megaparsecs away is receding at about 7,000 kilometers per second. A galaxy 1,000 megaparsecs away is receding at 70,000 kilometers per second. And this expansion is accelerating. Since 1998, we've known that the expansion of the universe is speeding up, driven by the mysterious dark energy that fills all of space. Whatever dark energy is, it's pushing the universe apart faster and faster. In the far future, the expansion will carry distant galaxies beyond our observable horizon. Their light will never reach us. They'll disappear from our view one by one, carried away by the relentless stretching of space. The universe itself is in motion, not just the objects in it. Space itself is moving, stretching, expanding. There's another form of cosmic motion that's even more extraordinary. Gravitational waves. In 1915, Einstein's general theory of relativity predicted that massive objects moving through space-time would create ripples in the fabric of space itself. These ripples would propagate outward at the speed of light, stretching and squeezing space as they passed. For a century, gravitational waves remained theoretical. Einstein himself doubted they were real physical phenomena. He thought they might be mathematical artifacts of his equations rather than actual waves in space-time. But in September 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected gravitational waves for the first time. The waves came from two black holes spiraling into each other and merging about 1.3 billion light-years away. Each black hole had a mass of roughly 30 times the mass of the Sun. As they spiraled closer, they orbited each other faster and faster, reaching speeds close to the speed of light in their final moments. When they merged, the collision released more energy than all the stars in the observable universe were producing at that moment, and most of the energy was in the form of gravitational waves. Those waves traveled through space for 1.3 billion years, stretching and squeezing every point they passed through. By the time they reached Earth, they were incredibly faint. They stretched space by about 1,000th of the diameter of a proton. LIGO detected this unimaginably tiny distortion using laser beams bouncing between mirrors, 4 kilometers apart. The detection was confirmed and the discovery was announced in February 2016. It was one of the greatest achievements in the history of experimental physics. Since then, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events, black hole mergers, neutron star collisions, and other cataclysmic events from across the cosmos. Gravitational waves are constantly passing through Earth, through you, stretching and squeezing the space your body occupies by amounts too small to feel but real nonetheless. Space-time itself vibrates, it ripples, it's never perfectly flat, never perfectly still. The fabric of reality shimmers with gravitational waves from events that happened billions of years ago in distant corners of the universe. And there's something even more fundamental. We've talked about space being stretched by gravitational waves and by cosmic expansion. But at the very smallest scales, space-time itself may be in constant fluctuation. This idea comes from attempts to combine quantum mechanics with general relativity, a unification that physicists have been working toward for decades, but haven't yet achieved. At the Planck scale, roughly 1.6 times 10 to the negative 35 meters, quantum effects should become significant for space-time itself. At this scale, the smooth fabric of space-time described by general relativity might break down into something chaotic. Physicist John Wheeler proposed in the 1950s that at the Planck scale, space-time would be a foaming, bubbling mess of quantum fluctuations. He called this space-time foam. In Wheeler's picture, the geometry of space at the tiniest scales is not fixed. It fluctuates wildly. Tiny wormholes and black holes pop in and out of existence. The topology of space itself changes from moment to moment. Space at the Planck scale might look nothing like the smooth, continuous fabric we experience at larger scales. It might be a churning quantum chaos where the very concepts of distance and direction lose their meaning. We don't have a confirmed theory of quantum gravity yet, so we can't be certain about the details of space-time foam. But every serious attempt to combine quantum mechanics with gravity predicts some form of space-time fluctuation at the Planck scale. Whether it's string theory, loop quantum gravity, or other approaches, they all agree that space-time at the smaller scales is not still. It fluctuates, it vibrates, it foams. Let me also mention the cosmic microwave background radiation one more time because it connects everything we've discussed. This ancient light fills every point in space. It comes from every direction. It has a temperature of 2.725 Kelvin. It's a bath of photons that pervades the entire observable universe. Every object in the universe, no matter how isolated, is immersed in this radiation. Photons from the cosmic microwave background are constantly hitting every atom, every particle, every surface, everywhere. They deliver tiny kicks of momentum. They transfer tiny amounts of energy. They ensure that nothing in the observable universe can ever be completely thermally isolated. Even if you could build a perfect shield against every other form of radiation and every other source of disturbance, the cosmic microwave background would still be there. It's the echo of the Big Bang, and it fills all of space uniformly. There is no place you can go to escape it. There is no shield that can block it entirely. It is the universe's permanent background hum, a whisper of energy that has been present since 380,000 years after the Big Bang, and will continue for trillions of years into the future. Every particle in the cosmos is bathed in it. Every point in space is suffused with it. Perfect isolation is impossible in a universe filled with this ancient light. So let's bring it all together. Let's look at the complete picture. At the smallest scales, quarks inside protons move at nearly the speed of light. Gluons are created and destroyed in a constant frenzy. Virtual particles pop in and out of existence in the quantum vacuum. Electrons buzz around atomic nuclei in probability clouds that never collapse to a single point. Atoms in solids vibrate at trillions of times per second. Molecules in liquids tumble and collide billions of times per second. Phonons carry vibrations through crystals. Proteins flex and breathe inside cells. DNA opens and closes. Molecular motors walk along cellular highways. At the human scale, tectonic plates drift across Earth's surface. Liquid ion churns in the outer core, generating a magnetic field. Earth rotates on its axis at supersonic speeds. Earth orbits the Sun at 30 kilometers per second. The Sun orbits the galactic center at 230 kilometers per second. The Milky Way falls toward Andromeda at 110 kilometers per second. The local group streams toward the Virgo cluster at hundreds of kilometers per second. The Laniakea supercluster flows toward the Great Attractor at 600 kilometers per second. Space itself expands, carrying galaxies apart. Gravitational waves ripple through spacetime. At the Planck scale, spacetime foam bubbles and fluctuates, and the cosmic microwave background fills every point in the universe with ancient photons that ensure nothing is ever truly isolated or truly at rest. There is no scale at which stillness exists. There is no place in the universe where motion stops. There is no particle, no atom, no molecule, no planet, no star, no galaxy, no point in space that is perfectly, completely, absolutely still. The universe is motion. From top to bottom, from the largest cosmic structures to the smallest quantum fluctuations, everything moves. Everything vibrates. Everything flows and churns and oscillates and orbits and expands. This isn't an accident. It isn't a coincidence. It's a consequence of the fundamental laws of physics. Quantum mechanics forbids perfect stillness through the uncertainty principle. Thermodynamics ensures that heat always flows and entropy always increases. General relativity describes a space-time that curves and ripples and expands. Electromagnetism drives the interactions between charged particles that keep atoms vibrating and currents flowing. The strong force holds quarks in their frenzied dance inside protons. Every fundamental force, every law of physics contributes to the universal restlessness. And here's what might be the most profound realization of all. This restlessness isn't a flaw. It's not a limitation. It's not something the universe has to endure. It's what makes the universe work. Without quantum uncertainty, atoms wouldn't have their sizes. Matter would collapse. Chemistry wouldn't exist. Without thermal motion, biological processes would stop. Enzymes wouldn't function. Life would be impossible. Without zero-point energy, helium would freeze, metals wouldn't conduct electricity, and the sun wouldn't shine. Without tectonic motion, Earth would have no magnetic field, no atmosphere, no protection from the solar wind. Without the expansion of space, the universe would have collapsed back on itself long ago. Motion isn't something that happens to the universe. Motion is the universe. It's the mechanism by which everything that exists is able to exist. Stillness wouldn't just be unusual. It would be catastrophic. A perfectly still universe would be a dead universe. No atoms, no chemistry, no stars, no planets, no life, no anything. The restlessness that prevents perfect stillness is the same restlessness that makes everything possible. So the next time you sit in a quiet room and everything seems perfectly still, remember what you've learned tonight. Remember that the atoms in the walls are vibrating trillions of times per second. That the molecules in the air are screaming past each other at over 1,000 miles per hour. That the electrons in every atom are buzzing in their orbitals at about 1% of the speed of light. That the quarks inside every proton in your body are moving at nearly the speed of light. That Earth is spinning, orbiting, drifting on tectonic plates. That the sun is racing around the galaxy. That the galaxy is falling through space toward a massive concentration of matter, hundreds of millions of light years away. That space itself is expanding beneath your feet. That gravitational waves from black hole collisions 1 billion years ago are stretching the space between your atoms by imperceptible but real amounts right now. You are never still. You have never been still. Nothing you have ever seen or touched or imagined has ever been still. Stillness is the one thing the universe cannot do. It is the one state that physics forbids. From the smallest quantum fluctuation to the expansion of the cosmos itself, everything moves, everything vibrates, everything flows, and it always will. That's not just how the universe works. That's what the universe is. a symphony of motion, playing at every scale, in every direction, at every moment, forever. And you sitting here right now on this spinning planet, around this orbiting star, in this falling galaxy, in this expanding universe, are part of that symphony. You are made of motion. You exist because of motion. And as long as the universe exists, the motion will never stop. Thank you for joining me on this journey into the deepest nature of reality. If you found it valuable, a like or subscribe would mean a lot. It helps me keep making these explorations. And remember, the next time everything around you seems perfectly still and silent, it isn't. It never was, and it never will be. Good night. And may you never think about stillness the same way again.